Okay, I guess we will get started, Abra. Okay, good morning and welcome to day 3 of the Java week and to this session on parallel programming made easier, ForkJoin. Yesterday, for those of you who attended Trent's talk, which was the technical keynote, where he talked about the new features in Java 7, he alluded to the ForkJoin framework, and he did mention that this is one feature in Java 7 that he strongly recommends all Java developers and practitioners to be aware of and then try and get their hands on this particular framework. So today we have Kavita, who's going to talk in detail about the ForkJoin framework. It was introduced as JSR 1.6.5. So I hear an echo. May I request folks who are on the call to go on mute? Thank you. So today we have Kavita Varadarajan, who is in the Java Technology Center development team and has more than 11 years of experience in product development, support testing, and then specifically performance engineering. She has loads of experience on Java performance engineering, and in her current role, she is a part of the JAX component, and in Java, she's in the development team for that specific component. So welcome again, everyone. This session is being recorded, and the recorded session would be made available after the talk on the community. Please join the community to be able to download the presentation post this talk. Thanks for your time, and I hand it over to Kavita for the session on ForkJoin.
Hello everyone, a very good morning to all of you. So today's topic is parallel programming made easier with ForkJoin. So let's start. The second slide here is the standard disclaimer, so I'll skip that and let's move to the agenda. So here's what we're going to cover today. First, we'll be seeing why is concurrency and updates to the concurrency packages very active now, and then a little background on the building blocks for a concurrent application. After that, we'll be stepping back a little and seeing how Java concurrency has done over the years. We'll then talk about the ForkJoin framework, which is the latest Java concurrency update, and how it is designed. I'll then go to a deep dive where we'll be looking into the implementation classes, and we'll conclude it with an example and a sample on, we'll go through how to write a ForkJoin application. I'll also briefly touch upon MapReduce algorithm, which is the Google search algorithm, and how it is different from ForkJoin. So that's all we have for today, and let's move on to the next slide. Okay, so concurrency, why it is very active now. You could see a graph here. The graph here shows the history of interchip introduction by clock speed and number of transistors. A green line here shows the number of transistors that is growing over time as with different Intel chips that are introduced, and the dark blue line here shows the clock speed of the different processors over time. So please observe that the clock speed here becomes almost flat around 2003. This is basically attributed to the block faced by the chip engineers owing to problems like heat, power consumption, etc. Even though you can see that the transistors graph is linearly growing, please note that there is a change. Around 2005, you would see that the increase in the transistor is coming through the multiple cores and not through a faster processor. So what does it mean to us as a software programmer? Well, the pre-performance lunch is over. We have to gear up ourselves to start writing better parallel programs. Over the decades, we have been enjoying performance improvement to our software without us doing any change. The boost is primarily caused by a faster code. But now, even though the speed is still increasing as it is to multiple cores, our software should be written to exploit the parallel running cores. That is, if I have a 2-core processor, each of 3 gigahertz speed, will my sequential program now double its speed? No. We have to write a program to exploit both the cores to the maximum. Moving on to the next slide. So we'll first define certain phrases that we'll be using during the rest of our discussion for this context. Let's define a concurrent application first. In this context, concurrent application is an application that has subtasks that can be run parallelly. What is a subtask? What is a task? Task is an abstract, discrete unit of work that can be run independently. And then what is a thread? A thread is a mechanism that can be used for running the tasks asynchronously. Okay. So let's move to the building blocks. So the 3 basic building blocks, we are not going to cover all the building blocks that are provided. The basic building blocks for a concurrent application are execution engine, program data, and task dispatcher. What is an execution engine? Execution engine is a framework for standardizing invocation, execution of the tasks, and the lifecycle management of the thread. Thread is the where the tasks are going to be run, essentially. And then a program data. What is a program data? Program data is a shareable data across the tasks in a concurrent application. So in Java's context, an execution engine is a task execution framework, and a program data is the Java support for thread safe collections like vectors, hash table, etc. And then we also need a task dispatcher where the tasks will be held on and then queued for operation. So Java provides different implementation of queues which can be used for this purpose, like queue, blocking queue, dequeue, etc. So let's just repeat these basic building blocks with respect to with a diagram, which is in the next slide. I'm moving on to the next slide. So you would see there a picture there with a thread pool, worker queue, and concurrent collection. So typically, we'll have our execution engine will be maintaining a thread pool and a worker queue. Thread pool will be holding fixed threads, which is available for service, and worker queue is a place where the tasks will be queued. If a executing thread wants to spawn another subtask, it will be submitting the task into the worker queue. If the worker queue finds that if the task dispatcher finds that there are idle threads which can take up a job, it will invoke the task into that thread. In between the threads that are executing the concurrent tasks, shared data, all of the running tasks will access the shared data as required, and the shared data will be held on concurrent collection. Moving on. I am now on slide 7. So now we'll see how Java concurrency has been over the years and how our basic building block frameworks are mapped to the Java language constructs that are provided. So here in this table, as we all know, we have Java concurrency framework or concurrency primitives available in Java language from its inception. But what is there in pre-Java 5 is what we're going to see now. Okay. So first, we'll see the first building block, which is task execution framework. There is no framework as such for task execution in pre-Java 5. So a task will essentially be an instance of a class that implements runnable interface which has a run method. The run method is what will be holding the main processing code for the task. And the main method will then be calling thread.start of a task for running the task. So you can see that the number of tasks that will be in a concurrent application is equal to the number of threads the task handles. So also that in between the threads, communication will happen through raise, notify, implement, etc.
Sorry for the interruption, but there is an echo that the attendees are getting on their audio cast. So if there are folks who are on the phone and also on the Lotus Live audio cast, would request them to either log off the call or use the audio cast so that the echo. Thank you.
Okay. So we just saw that how the task execution happens. Then the share we come to the second framework, which is shared data. So for shared data, previous Java releases had space collections like vectors, hash tables, lists, etc. All of them use a single mechanism for concurrency, which is a synchronized keyword applied to all the access methods, which means that there is one common log that every task has to fight for accessing the data. Next is task dispatching. There is no framework for task dispatching. There is no queue. So only way work dispatching happens in pre-Java 5 days are to create a thread whenever a task needs to be done. So the issues are more glaring here. The issue is that even though Java concurrency primitives are there, they are too primitive or too low level. The thread creation, task management, task delegation are all part of the application. As you know, thread management cost is very high, and there is no thread queues defined here. So every time a thread needs to be a task needs to be done, a thread needs to be created and then destroyed once it is completed. So there is lots of management cost here, and the only bread and butter of concurrency is synchronized keyword, which is very poor in performance because it's a common log. Okay. And another disadvantage here is, as I told you, that the task will be defined as the instance of an object that implements the runnable interface, and the runnable interface does not provide an option to return a value, which means that there is no way the task that is spawned can return a value back into the main program. For example, if you have if your computation or a program requires a value to be returned, you have to have that as well as a shared data. So these are the limitations that we had in earlier Java. Moving on. Now we have seen all the issues. So when the Java 5 came up, all these issues are addressed through a magic package, Java Util Concurrent. So let's see how Java Util Concurrent library that was that was implemented, designed by Dagli, is addressing these problems. First, our building block task execution. Java Util Concurrent package introduces a task execution framework called Executor Service. The Executor Service provides scheduling, that is timed execution of the tasks. We can specify a time after which a task needs to be run and a repeated execution. It also provides complete thread lifecycle management by using thread pools. And we can also specify the order of execution, that is, you can specify whether your task needs to be scheduled only for or before ordering. So all these are provided by the framework. In Java 5, the task is again an instance of an object that implements a runnable interface or a callable interface. Callable interface is a new interface that is added in Java 5 that supports the problem that we saw in the previous release, that is inability to return a value. So callable interface supports two things. It now provides a way to return a value back to the main program, main thread that calls, and also supports asynchronous completion. And another, for the asynchronous completion, what Executor Service does is it produces an object called future. Future, again, is a new interface that is introduced in Java 5 that is for holding the result of an asynchronous completion. So moving on to the next one, which is shared data. So as we saw in the previous release, most of the thread safe collections are provided by synchronized keyword, that is synchronizing the whole method with a synchronized keyword. Here, the concurrency data structures are going to the next step. We have data structures like concurrent hash map and copy and write list, where instead of providing a common lock, we have fine-grained locking mechanisms, which will be controlling access per thread and not per method. And there are also lots of strategies for synchronization based on the type of access. Like if two threads are going to read, there will be no locking performed. So the strategies like this are incorporated so as to reduce the synchronization cost. Moving on to the task dispatching, there are lots of queues implementations that came with in the Java ITIL concurrent package for dealing with better queuing operations like blocking queue, dequeue, queue, etc. So as we see that it's a big, as you can see that this is a big step when compared to the previous concurrent implementations. But there are a few drawbacks. That is, number of tasks, as you see, cannot be altered at runtime. You have to divide the tasks or submit all the tasks before you submit them. And the other and more important drawback is application of this framework to recursive style of application. So what happens is a recursive style of application or divide and conquer style of application would require you to span the task as you go along. You can well implement that using a callable interface by using a submit method, which is the asynchronous submission of the task. But what happens is when you submit, when a submit happens, when a callable calls another callable, it will wait on the previous callable, which means that the thread itself will be marked as wait, and it won't be able to execute other tasks. So that is a scheduling gap that was there in the executive framework, because of which the recursive style applications suffered. Moving on. So the issues that you saw in the previous slide form the basis or need for the ForkJoin framework. So like a producer-consumer style of problems, the recursive style of resolving is a common approach for many scientific problems like merge chart, Fibonacci series, etc. So the framework is designed for supporting such style of problems. First, let's see the divide and conquer approach. So divide and conquer approach is very simple. You would see the picture in the right side explaining that. So divide the task as much as into two till it becomes small enough to be handled at once. And that's the basis for a divide and conquer. And the picture on the left is the representation of it for the math lovers. The entry node entry node is a entry point where the job will arrive, and it will be split into different nodes. Subdivided into different nodes, and then at the end of it, it'll be joined through the join node. Okay. So now coming back to this framework, this is introduced through JSR 166Y, which is now part of Java 7. It's implemented using by extending the executor framework for recursive style problems. So it basically tries to fix the gap that we were seeing in the last slide, which is the ability to run add the subtasks over time, and also to not wait when a callable interface is again calling another callable interface. So those are the things that will be addressed. So first let's see the basic what happens on a fork and what happens in a join. Fork, when a fork is called, it starts a new parallel fork join subtask, and when a join is called, a current task is not allowed to proceed until the fork task is complete. So these two are the basic mechanisms. Let's go into the design, which is in the next slide, to make it a little more clear. So let's look at how the framework is designed. We have a pool of worker threads that is established, which is typically equal to the number of cores in the processor. And then we have tasks that can be spanned at runtime. This is how the scheduling works. We have a thread pool, and each of the worker thread in the thread pool has its own worker queue. On a fork, the worker queue here is a doubly ended queue, which means that you can do LIFO as well as FIFO operation in that queue. Whenever a fork is called, the subtask from that thread is pushed into its own worker queue. Worker thread process in LIFO order, which means the youngest first order. When a worker thread has no task, like in the picture if you can see, the TN has no, his worker queue is empty, WN is empty. So in that case, it can go and steal the job from another worker queue, and that happens in FIFO order. So as you could see that because the processing happens in LIFO order, that is youngest first order, and the stealing happens in FIFO order, there is a very less chance of contention. The contention here can happen only when only when the queue has only one element. So contention handling is minimized because of this approach. Also, we are also minimizing the probability of having an idle thread when there is a task available. And another important point to note here is because the jobs are you will notice, push and then the youngest job is taken by the thread. Whenever idle thread is trying to steal a job, it will always get a bigger chunk for execution. And another scheduling mechanism that is employed is when there is a steal tried, but there is a failure because of any reason like contention, or there is only one or two tasks available, or any other reason, the thread that is trying to steal sleeps. It is to avoid further contention and hence the loss of performance. Hope this is clear. I'm moving on to the next slide. So this is an algorithm. Basically, it says how you should be having your ForkJoin task main method. So if you want to write your own ForkJoin task in the divide and conquer approach, how your algorithm should look like. So first you have to see what is your portion of the work, task granularity, which is identify the small portion of work that can be done sequentially. This will be doing through some monitoring. So once you do that, like for example, if you are doing starting an array with say 10,000 elements, you can pick some 50 elements as a portion of work that can be done sequentially. So here is what your method should do. If a portion of the work is small enough, do the work directly. Otherwise, split the work into two parts, invoke both of them into two parallel tasks, wait for them to complete, and aggregate the results. So it's that simple. Moving on.
Hello.
Yeah. Yes.
Hi. This is Mantesh here.
Okay.
One doubt. Okay. Currently, in the current architecture in Java 6 and all, we have executor service where we can even submit the task which extends runnable interface or thread.
Yes.
So in this particular ForkJoin, internally it is actually allocating the task to a different core itself. If I am having 4 CPU machine, there are 4 CPUs. So instead of creating 4 threads in the one CPU, it creates 4 threads in different CPUs?
No, we do not have control over the course, but I think we can probably, I'll address this question, but we probably can take the questions at the end of the session. But it doesn't happen that way. But what it does is, it creates the, if it is a multi-core processor, the fixed thread pool will have, if it is a two-core processor, the fixed thread pool will have 2 threads. And we will try, based on the number of tasks available, we will always try to have both these threads 100% in the execute mode, which guarantees us that both the threads will be running in a exploiting the code to the maximum.
Okay, both the cores to the maximum instead of one.
Yeah, correct.
Fine. So when we are creating worker pool, it is like if we have 2 cores, then 2 workers will be there, is it, in the pool?
2 worker threads, yes. That is the default behavior. It will take the number of CPUs as the default. You can try and change and see how it behaves, but the optimal suggested thing is the number of CPUs, number of cores. Okay. So moving on, now we have seen the basic framework and how it is designed, and the next part is the main classes. So we will try to see what are all these main classes and how they map to our framework. ForkJoin pool is a task execution framework or the execution engine, which is the core part of the framework. As explained in the design slide, this also implements queuing and scheduling. There are a lot of monitor methods that can be used as well for querying the framework, like get steal count, which will tell whether how many times a steal has been tried, etc. So these are the monitor methods that you can use to see whether you are employing the ForkJoin framework to the fullest. So task execution framework, what it is? It is an executor service plus the advanced scheduling and queuing disciplines, which is work stealing. And we also have the status check methods, as I said. So and then comes the ForkJoin task. ForkJoin task is the abstract base class which our tasks will be running. Like our tasks will be the subclass or object of this ForkJoin task. So ForkJoin task will start its execution after this task is submitted to the ForkJoin pool. So the primary methods that are, as the name indicates, as fork and join. And the invoke call is another method, which is to do this in a synchronous fashion. The invoke call will fork and then wait for the forks to complete. So you can say that info call is fork plus join in one. And as I said, ForkJoin task supports asynchronous completion. So when we support the asynchronous completion, the task, we should have some way to get back the result, which is done by implementing the future interface. So ForkJoin task implements the future interface, and which supports, the executor framework, which is the ForkJoin pool, will return the future object on submission, and the future.getOff can be used to wait for the asynchronous results. So even though the ForkJoin task is the base class which can be used as is, we have 2 subclasses for ForkJoin task, which is recursive task and recursive action. Recursive task both are the base class, subclasses of ForkJoin task with only one difference. The recursive task has the ability to return the result, and recursive action has it returns null. So between the recursive task can be used in scenarios where you would want to return the computed result back to the main thread. For example, if your thing is to compute the size of a graph, where you would want to return the size back to the main method. And the recursive action can be used in scenarios like start, where the array that is going in as input will be the output as well. The next diagram. Okay, it's taking a little longer time to load. The next one is the class hierarchy. So I'm just trying to put these classes in context. And we can reiterate how they are arranged. I don't know, it's not coming up. Okay. I'm not sure whether you're seeing the slides. Should we pass for a few minutes? Okay. I'm assuming others are seeing the slide and only I'm having the problem.
So can somebody quickly confirm? Okay, we see some confirmation on the chat that people are able to see, so I guess we can move on.
Okay, so here is the class diagram for the main classes. Okay. The ForkJoin pool, as you can see, extends the executor service and implements all the methods that are there in executor service, like invoke, execute, and submit. Invoke is a synchronous, it's a synchronous call, and execute and submit are asynchronous calls for the call for the same functionality. So invoke will do invoke the task and wait for it in a synchronous manner. Execute will start the task in asynchronous way and return back. The submit does the same thing, but it has the ability to monitor the result. So when you submit the task in an asynchronous way, the executor returns back a future object which you can use for monitoring the result. Okay, so the next one is slowly. Okay, the next one is the ForkJoin task. As I said, it implements the interface future so that it can monitor the results when it does asynchronous completion, and it has two subclasses: recursive task and recursive action. Recursive task has the ability to return the value, and recursive action has it doesn't return a value.
Now departing.
Okay, moving on. So we'll just now try to illustrate the use of the ForkJoin framework with a simple example. So I thought merge sort could be the a very simple example, and also we all know that merge sort is divide and conquer approach for sorting the problem. So it's a very straightforward choice. So let us take let's look at this method. I have not put the whole code, but only the snippet of the code here. This is the ForkJoin task. So here you see that there is a size underscore threshold. The size underscore threshold is the task granularity that I was talking about. So we have to fix the minimum size for the work, which we think can be done sequentially. So we have just fixed it as 16 in this case, and merge start is the main method. You see that first we are doing if the size of the array is less than threshold, will not split the task anymore. Will directly execute it, which is started. And if it is not the case, we will subdivide the problem twice and then recursively call the main method. One important thing to notice here is, I have not put the whole code here, but even though we are using an array here, the array input could come from any of the I/O devices. And one main thing to avoid when you are using a ForkJoin framework is to direct handling of I/O inside your main method. So if at all you are reading your tasks from a array from a file, please make sure that it is you are using a buffer reader or some other way to put it all into the memory before you start accessing it. It is not. ForkJoin framework doesn't perform
Kolkata.
Doesn't perform to the maximum when you are using I/O operations inside your task. It's true for any multi-threading operations, but I'm just stressing that here. So as you can see, the threshold we have to fix the threshold, which is the task granularity, which will be different for different problems. And based on the size threshold, we will decide whether to split the problem or not. Once we split all the problems, and the last step will be to merge. Okay. Moving on. So we'll see the ForkJoin implementation of the merge sort. As you can see here, the first, it is the same method. The main method is now into part of the compute. Compute is the main method for recursive action, where you have to keep the actual code. Okay, and so there is no change there, but the main change is in the main program, you are defining a ForkJoin pool. I have just given here the new we are instantiating the ForkJoin pool with n threads, which is the available processes. I've just put it to make it more explicit, but even if you don't put it, if you just use an empty constructor, the default behavior will be to use the number of cores in the processor. So if you are having a 2-core processor, it will be having 2. It will be taking in 2 as the default value. And the start task is the main task, that is our ForkJoin task in this case. And you notice that I'm using recursive action here and not recursive task. That's because our merge start is using an array, and we don't have to return a value. And okay, and inside the main method of compute, we are using invoke call. You see that the two recursive calls that we saw in the previous slide is now replaced by one invoke call. What invoke call does is it forks 2 tasks and then wait for it to join. So this is a synchronous way of forking, and then you see that this will repeatedly call the submit the new task to the framework. Okay, it will repeatedly submit the task back to the framework till all the tasks. Okay, the invoke call will, as you can see, will repeatedly submit the task back to the executor queue. Okay, so that's all I have here. If you have any questions on the example, I can take it now, or otherwise we can go to the next section, which is to compare the MapReduce, which is the new, it's not new, I'm sorry, Google search algorithm, and the ForkJoin, and how they are different.
Is there a question on the discussion so far?
I have a question on the merge. So that essentially can only happen on one single core, is it right? Because there's a dependency where it has to wait for all the tasks to end. So potentially
correct. Okay. So if you can visit back what I was talking about in the design. So I think you're talking about the waiting for the join or the merge.
No, I know that we're waiting for all the subtasks to get over.
So that's what. When they are waiting for the subtask to be to get over, the task will not be in any of the threads. What the ForkJoin scheduling does is, whenever it forks the job and it has to wait for the result, in that case it will push the waiting task back into its queue, and it will not process it until is done off. There are methods through which we can identify whether all the forks that are spawned from this task is complete, which will be denoted by is done off method. So till that method is called, the task will be put back into its scheduling queue, and other tasks which can be executed will be executed. So the particular task will be waiting, but the threads won't be waiting.
Yeah, that is one aspect. Another is once all the subtasks are over, the actual aggregation or summarization task, now that which you suggested using merge, that anyway has to happen in one thread, or can we do?
No, it will happen. It will happen as a part of different tasks, right? Because say you see the, in this scenario, if you see, there will be different tasks that will have to merge, isn't it? Like 1,000 will, you assume there is an array with 1,000 entries, and we are splitting it into two till it becomes 50. So there we'll have to do lots of merge, which will be part of different tasks.
Right.
Is that clear? I won't. Assume, okay, let's take a smaller example. Say there is 100 elements and 25 is the threshold. We will first divide it into two. ForkJoin task 1 will have 50 elements and 2 will have 50 elements. Okay, so it will still see that it is not good enough to be executed, so it will split again. So into 4 tasks. So now we have 6 tasks. Okay, the first 2 tasks are waiting on tasks 3, 4, 5, and 6. Right. So the first 2 tasks will be pushed into the queue, and the threads will start executing 3 and 4. Once 3 and 4 are complete, the second task will be taken back. So if it is split into 2, if it is split into 6, there are 2 merges which are happening parallelly. The final merge, of course, will happen once, which will be part of the main task. So it will still not be merge will still not be a single, happening in a single task. We will do merges multiple times. Does it clarify?
Yeah, I'm still looking in the data part where in this case the array which you have done, how are you returning it back to the core which is concerned?
Here, as I explained here, we are not returning back. We are using recursive action framework here, which is the resultless implementation of ForkJoin task. We do not have to return back because we are sorting an array in itself. We are just using a temporary array for the purpose, but the results will be in the input itself. So there is no need for returning. If you want to, if your application logic demands something needs to be returned, you can use recursive task. Your static class start task now will extend recursive task, and then you will be using submit, and you'll be returning back in your method the results.
So I think the question is using shared data, and you're not actually passing data. You're not actually doing message passing like how you would do in an actor-based model, right? Where you would not worry about shared messages and just pass messages to each actors, and they will basically send you the return data. And if those actors abruptly end, then you basically spawn off another actor and then send that message back to it. What you're saying is you're actually working with shared data here across all these threads. I think which you had earlier specified in your PowerPoint. Okay.
Yeah. So this is a very simple example. We have to take an advanced session for seeing how we can incorporate your request.
Okay.
So it's a very simple example to just explain how the ForkJoin can be implemented.
Okay. In the interest of time, I guess Kavita can move on, and we will take some questions towards the end.
Okay.
I see there are some questions on the chat, but once you're done with your remaining slides, we can take those.
Okay. So I'm into my slide 16, which is map reduce with ForkJoin. We have, if you are following concurrency-related blocks, you will be seeing that there are lots of questions around is ForkJoin same as MapReduce and how it is different from MapReduce, etc. So that's how we thought we'll have a slide briefing about that. So what is MapReduce? MapReduce is a software framework that is introduced by Google in 2004 for supporting distributed computing on large data sets. So, we will be Google's index of the World Wide Web now is generated by this MapReduce algorithm. So how it does is, like when it will like ForkJoin, there are 2 steps. there is a map and there is a reduce, and it does use divide and conquer style approach like ForkJoin. But there is a difference in terms of where it is, applicable. This is map. Okay, let me explain the map and reduce first. What map does is it takes in a key value pad, which is probably the entry that you want to search, and then it tries to partition the problem into many sub-problems, like similar problems, and it will generate many key value pads which look similar to that of the initial input, and then those key value pads will be sent to different nodes, which here are different machines, different parts of the cluster, which will be trying to solve the problem and generate the results. And at the end of the chain, once all the sub-problems are resolved, the reduce step will try to take all the answers and collate. So as you can see, this problem, it is these both algorithms are now applied for different contexts. The platform for ForkJoin is a single JVM, that is it is applicable for a concurrent application that is running in a single machine with multiple cores. Whereas MapReduce algorithm is applied for a cluster-based distributed computing, where the work will be distributed across different systems. And in terms of recursion or subdividing the task, ForkJoin recursively subdivides. It keeps on subdividing your problem until the problem is small enough. And whereas MapReduce has one-time forking. In the map step, initially it maps the problem into as many sub-problems as possible, and then it goes on to solving them. And in terms of work distribution, there is as we have explained before, there is a work stealing logic, and there is the threads can talk to the worker queue and steal the job from a different queue. And there is no internode communication in case of MapReduce. And in terms of scalability, how scalable it is directly proportional to the number of cores or number of CPUs in case of ForkJoin, and it is directly proportional to the number of nodes in case of MapReduce. So that's a brief difference there. And I have also added the MapReduce algorithms and different references that you can find useful in the references section that you can later look into. So I'm moved on to the summary slide. So here is what we have covered today. We first saw the arrival of multicore and why it is very important to do a better parallel program today. And then we saw the building blocks for the concurrent program, which is task execution framework, worker queue for holding the queuing operations, and thread space collections for storing the shared data. We also briefed upon the Java 5 executor framework, which is executor service, callable, future, etc. And then we talked about ForkJoin, its design, and also how it is implemented, and we concluded with the ForkJoin, MapReduce, which is we concluded with MapReduce as a ForkJoin comparison. So that's all I have. Please feel free to ask any questions.
Are there any questions?
Yeah. Again.
Yeah, please go ahead.
Yeah, I think the question was similar to on the same lines. So if I have if I'm paranoid about message sharing. Sorry. Hello.
Yeah, please go ahead. There's some background noise, so folks on the phone, if you could go on mute, please.
So,
unless and until it is the person who is asking the question. Please go ahead.
my question again is, in this ForkJoin, can I do message passing instead of, say, doing message sharing? Because if I have to, say, a large vector or collection, if I want to share it in memory and I want all these threads which are running on my multiple cores to share it, I may have some inconsistency issues also. So can I implement message passing here, where each thread or each task is given its own data, and I get back the data itself, and if that task, say, abnormally ends, I can respawn that task.
I'm not getting the question completely, but you are trying to talk with respect to threads. But our ForkJoin design recommends you to split them into tasks. We do not have, like when you are doing a ForkJoin task framework, you are not controlling the thread, you are controlling the task. So if you are asking, can I have task-specific data, you can have task-specific data, and you can use your compute method and return. As long as you can communicate to the return parameter of your task. You can use recursive task and return the value or return the result of your computation back to the main task through the return method. And other than that, there is no way. There is no specific way for passing the message.
Are there any other questions?
One question from me, Prashant here.
Go ahead, Prashant.
Yeah. Do you have any sort of a performance comparison between all these approaches? The initial normal thread mode of approach, the second is the concurrency approach, and then the ForkJoin approach.
Okay, we have multiple articles and blogs in the concurrency framework which talks about these things. If you can send me a mail, I can pass that over performance between these. We have slides which we can share. But it is not from us, and I have seen, there are lots of blogs and even entries in developer work which has these comparisons and performance statistics. I think there is one from Dougley himself talking about the framework.
So if you could just post the references on the community, please.
Yeah.
Okay. We still have some time to go, so we can take a few more questions if there are any. Okay. I'll take it that there are none. But as we have been saying in our webinars, we have the message board. If there are any questions or you need more information on any of the things that we are discussing or anything apart from that related to Java technologies, please feel free to post them. We are running a live chat tomorrow morning starting 11 a.m., which will run for 2 hours, where we will have experts from the Java Technologies Center available to answer any questions that you may have. Apra has put up a link there where you can post your questions. So again, I would like to thank everybody who took time this morning to attend this talk. Thank you, Kavita, for taking time to discuss the ForkJoin framework. Today, just a reminder, we have 2 webinars. There is a webinar in the afternoon on performance tuning by pros, which would be delivered by Chris Bailey, who is the Java Service Architect for IBM's Java. And he will cover a gamut of topics related to Java performance, right from tips on what things you need to take care from a performance perspective when you're developing applications, tuning the Java runtime, and also discuss some interesting examples where he'll use the tools that are available and show examples and illustrate how these performance problems can be debugged. So please don't miss that session. We will look forward to you attending that session. So please be encouraged to join that session. Tomorrow, we have a session in the afternoon again at 3:30 p.m. India time, where we will have Graham Johnson, who is the architect for Java on Cloud, who will deliver a talk on optimizing Java for cloud environments. So, the registration is open for that, so please go ahead and register. Thanks once again. These slides and the recording would be available post this call on the community. Join the community and then download. We appreciate your time and look forward to you in the subsequent sessions of this week. Thanks.
Now departing. Now departing. Now departing.
Rishmi from Chennai.
Now departing.
Hi, this is Venkat Singla.